Okay, cool, great. Okay, in here, let me see if I can find the. Thank you so much for having me over. Thank you for the introduction. I'm really excited to be here and more things that we don't want on the screen. Okay, here we are. All set to go. So today I'm going to be talking about certain properties of black hole accretion flows, particularly the turbulence of black hole accretion flows and why it matters for the way we model these accretion flows, as particularly with the interest of like radiatively inefficient flows as seen by the Magnetohydrodynamic telescope, Satapathy stage star and MHD. Okay, so let's get started. This is work in collaboration with Magnetohydrodynamic with the postdoc which is government vessels. So okay. So black hole accretion flows, modeling these flows are inherently challenging, right? Oops. Yes. Okay. Modeling these flows are inherently challenging, and these challenges mostly arise from this problem of scale separation. Scale separation is widely known across all astrophysical systems and all systems of plasma, astro and terrestrial, but it shows up in these black hole accretion flows as well. In particular, if you look at it this way, if I draw a typical power spectrum of how a black hole accretion flow looks like, we have to the left end the global dynamics of the accretion flow, right? So these global dynamics are numerically well studied using global general relativistic magnetohydrodynamic simulations. The simulations here shown on the left. However, the processes that determine the structure of the image are radiative processes due to the electrons in these flows, and the physics of like what determines the electron temperature or what determines how these things radiate occur at the much smaller scales, the dissipation scales of the plasma, which are like 10 orders of magnitude smaller than the scales of the global dynamics, right? Now, numerical studies on the left are very important to understand how things move around these black holes, but we would not infer much about how the structures in the black hole are supposed to look like, supposed to move, or even how the spectra look like, unless we know the right-hand side of the spectrum, right? So, in order to facilitate the bridging of scales, what we need is subgrid models. Subgrid modeling is a very well-known technique. We need to study the right end of the spectrum and put it back into the left end in a self-consistent way so that we are actually capturing physical dynamics. Okay, and subgrid modeling is pretty important in inferring how images and spectra in these sources look like. And some of the work exploring subgrid modeling, the impact of subgrid modeling in black hole accretion flows has been done by Jason in very recent years, and in parallel with many other studies that explore various heating mechanisms on the right end of the spectrum that are potentially responsible for heating of the plasma in these sources, and the implications of how we infer observations from these. So what we are looking at are images obtained from the same simulation at two different wavelengths in the columns, and two different subgrid modeling capturing two different pieces of physics, right? So collisionless damping is one potential source of heating and acceleration in these sources, and so is magnetic eddy connection. So depending upon what you put in your global simulation, you infer things differently. Not only do the images look different, the spectra also look different. So there have been deep studies comparing, okay, how does subgrid modeling affect our spectra, what are the potential mechanisms that might cause heating depending upon both global and local dynamics. In this talk, I'm going to try to bridge the scale separation, self-consistently model, like build frameworks for self-consistently modeling these emission sources pertaining to collisionless damping. So the focus of today's talk is going to be the heating mechanism of collisionless damping. So collisionless damping is fundamentally something known as wave-particle interactions, the mechanism of heating the particles in the plasma are occurred by means of wave-particle interactions. What are wave-particle interactions? Well, so if you zoom into the right end of the spectrum, this is what it looks like. If you look at a distribution function, there's a little animation showing how wave-particle interactions work. The distribution function on the plasma is shown on the right, and if you turn on a wave, turn on an engaged wave in the plasma, the particles with velocities equal to the phase velocity of the wave resonate with the wave, and it causes a little kink in the distribution function as you see on the right. And that kink leads to effective heating of the plasma, and that is exactly how collisionless damping works. So now we are looking at the fact that there is a wave input into the system, it's causing some heating, and that is eventually what will lead to determines the physics of electron heating. And one key element in this is that there is a wave input into it, right? So what is pumping in waves into the system? Well, it's actually the left end of the pump spectrum, right? So turbulence is driven by global dynamics in accretion flows and pumps energy into these magnetohydrodynamic waves. And these waves are what cascade down to much smaller scales and undergo these collisionless damping processes or particle resonances that pump in heat into the atoms of electron, leading to observational sequences. Our goal here is to pitch the scale separation by means of this picture, in particular, looking at the left end of the power spectrum. Right? How does the question that we are asking here is, how does global shear power injection inject energy into the magnetodynamic wave cascades, and which eventually go down and heat up the particles? So if you go back to plasma 101, magnetohydrodynamic waves come in three flavors, right? We have the fast magnetosonic waves, slow magnetosonic waves, and alpine waves. So these waves are expected to be decoupled energetically decoupled in the regime of plasma, in the plasma of interest, which is very anisotropic plasma, in the presence of large-scale magnetic fields and the plasma fields. This decoupling gives us an avenue for extrapolating the scales from the left end to the right end in a self-consistent manner, meaning that if we model the left end of the power spectrum, there is no other characteristic scales in that which these waves interact in a significant manner. So as soon as we capture the injection scales on the left and capture how shear power injection injects energy into these fast, slow, and alpine waves, we can take those properties, extrapolate them to the small scales, and then model the microphysics using kinetic scale simulations, model and electron heating, and infer how those will lead to observational signatures. Okay, so the problem that I'm addressing in this talk is kind of clear right now. I'm looking at the left end of the power spectrum, asking the question, how does shear power inject, how does the shear inject energy into the normal mode magnetohydrodynamic cascade wave cascades. So we have global simulations of the left end, and I'm actually not going to solve the normal mode decomposition in the global simulation, but I'm going to cheat a little bit. I'm going to zoom into a little patch of this simulation. So this is known as the local approximation or the local shearing-box approximation. Many of the people in the audience here work on turbulence in the local shearing-box, particularly the magnetorotational stability is captured in these local shearing-box approximations very well. So effectively what you do is you take in a little patch of the MHD simulation, you zoom in, and I'm going to ask the question, how does the normal mode decomposition look like in this box? So one big advantage of this is that you can go to a scale, you can adjust the scale of the box as necessary, with keeping in mind the scales of interest in the global simulation. And the other thing is we can resolve the properties of the turbulence very well in a global shearing box. We can literally zoom in, right? So local shearing box simulations, what is the numerical decomposition? Is that question. Okay, so I'm going to simulate a local shearing box now. So I zoom in, take this box, radial, azimuthal, and vertical directions are shown. The field shown is radial velocity, and I shear this box. Shear is what drives the turbulence in the system. So I shear this, and it's in the radial azimuthal direction. The shear as expected in computations flows. And I have a mean magnetic field, which is relevant to the black hole accretion equations, primarily azimuthal fields with weak vertical field components expected that drive the vertical magnetorotational modes. I said magnetic fields like the plasma beta parameter, which represents the strength of the magnetic field with respect to the gas pressure, relevant to what is seen in black hole accretion plates. And I let this box run. So what we see in this box are the linear magnetorotational modes. Most of the channel flow-like structures are the linear MRI mode. And these linear modes are subject to parasitic instabilities. And the parasitic instabilities break these linear modes into a fully developed turbulence, right? So it's a turbulence with this characteristic shearing structure, as you can see, like structures move along the direction of the shear, but effectively it's a turbulent system. Now, this turbulent system causes efficient angular momentum transport, as many of you know. And the question I'm asking here is, what is the normal mode decomposition in this turbulence? What fraction of it lies in the fast flow of the turbulence, right? So, without going into much details of the specifics, I'm going to make a claim that fast waves are fundamentally compressible modes. So, and on the other hand, magnetorotational instability is a fundamentally incompressible instability. You do not need density perturbations to drive the MRI or the MRI to develop, which means that the fraction of fast waves that we see in this turbulence is negligible. It arises from the compressible nature of the waves. This turbulence is expected to be primarily slow wave and now let's ask the question: what is the split between these slow and unpaired waves? It's typically assumed in subgrid modeling so far in black hole accretion flows that the waves generated in these flows are primarily unpaired waves. But if we look at it, like try to actually solve the problem, as you will see, that is pretty much not the case. So in order to find the slow to unpaired wave ratio in this, I'm going to look at what exactly slow waves and unpaired waves look like in any system, any MHD system. Right? Again, a very basic picture of what are slow waves and what are unpaired waves, plasma wave. So slow waves and unpaired waves are set by the polarization of the displacement of these of the structures in the system, right? So slow waves are the waves that encounter displacements along the mean magnetic field. So the magnetic field is what sets these normal modes, and slow waves are effectively longitudinal waves. They are sonic waves, magnetosonic waves, right? So they're waves having parallel displacements, and this cartoon is a representation of how a single slow mode would move. Like a particular slow mode will move along the mean magnetic field with displacements parallel to the mean magnetic field. That is the displacement. The unpaired wave, on the other hand, if you have a picture of an unpaired wave, it is a wave on a string, waves on a string, right? So the magnetic tension is what acts like the string tension, and these are transverse waves on the other hand. So they have displacements perpendicular to the magnetic field in an incompressible way. They are like divergence-free perturbations. So this is pretty much all I need to know the normal mode decomposition of any turbulence particularly. So I can compute the decomposition now numerically using this information. There is like this is the parallel displacements is a limit of an anisotropic plasma. I can do this in general in the Fourier space, but there is more to it. Not only can we compute numerically what the slow to unpaired wave ratio is, but there's also key physics that goes into this. So as you can see, the mean magnetic field in these systems are expected along the big family azimuthal, which is also aligned along the shear, right? And so are the slow waves because the mean magnetic field is aligned along the shear, which means that the shear actually injects energy directly into the slow waves. So it literally comes from the polarization of the waves set by the mean magnetic field. Well, what about the alpine waves? Because they are not along the shear. Remember that this little patch of the accretion flow is moving around the black hole, right? So when you zoom into this patch, you will have to consider a Coriolis interaction. So the waves are being driven locally in this little shearing box, and it is this Coriolis interaction that takes some of the slow waves and puts it into the deposits and into the alpine waves. And this is exactly the physics that goes on into determining the numerical decomposition of EMI turbulence. And using this, not only can I numerically compute the slow-to-alpine ratio, but I can analytically derive what this normal decomposition is. So, and here is the expression for the slow-to-alpine wave dynamic ratio. As shown, it depends on the physics of the shear and Coriolis force. It can be inferred using the global Maxwell's and Ferriman's stress tensors. These stress tensors are what cause injection of energy into the system, and also they cause angular momentum transport. So dynamics of these stresses have been well studied with the magnetorotational stability. Not only do they impact the global scale transport of the flows, but also they impact plasma physics. They impact plasma physics by means of how they drive normal waves in MHD turbulence. Okay, so this is all there is to the problem. So slow-to-alpine wave dynamic ratio depends on the stresses, and there is a dependence on the shearing rate. Shear is what injects energy into the system, and it appears in our expression for the ratio in terms of that variable Q. Okay, so having put all of this, what does it mean? What are the numbers? So what is the slow-to-alpine wave dynamic ratio? Remember that there's no fast waves in this, so fast waves are 0. What is the slow-to-alpine wave dynamic ratio in MRI-driven turbulence? MRI-driven turbulence, if there's something that will help you to take away from this talk, it is the fact that MRI-driven turbulence in mid-plane accretion regions is expected to be slow rate oriented. It comes from the injection power, it comes from the injection physics and numerical computations based upon the Maxwell's and stress tensors. So we have a huge library of simulations spanning the parameter space, spanning different shearing rates, having different mean magnetic field stress. And what we see here is the slow-to-alpine wave dynamic power ratio as a function of Q for different values of plasma beta, magnetic field strength at each shearing rate. And this is usually slow and alpine waves are equal in power. As you can see, all of these numbers are way above, right? So as expected, because the direct injection is into the shear by the shear to the slow waves. It has a dependence on the shear. It has a strong dependence on the shear. It has a weak dependence on plasma beta. Plasma beta is a magnetic field strength, and it comes from this weak dependence on plasma beta comes from the fact that the mean magnetic field does not directly impact the physics as much, but it pretty much sets the polarization of these waves. It sets what is a slow wave, what is an alpine wave, and because it's primarily azimuthal and along the shear, that's all there is to it. That's the role of the it's.
Is this time average toroidal beta? Is this initial toroidal beta? Is this post-linear growth toroidal beta?
It is initial toroidal beta, but the final state toroidal beta is comparable to it. So the cascade is passed each past the main magnetic field. Like the perturbations that we capture in the shearing-box are of the order of lower than the initial magnetic field.
And you see this with this toroidal field, or?
Yeah. So if I initialize it with a toroidal field, you get these numbers. Even if you don't initialize it with a toroidal field, even if you just have a purely vertical field, you can compute the normal mode decomposition numerically. And because and these numbers are pretty much the same. The reason this happens is even though there is a weak field, the shear causes the structure, the magnetic field structure locally as it is at any point. So even in a shearing box, if you take a little patch and do the normal mode decomposition, then that's exactly what you get. At least this has been verified both by us and both by, as well as by one other group that studies this problem. Yeah. MRI is slow wave dominated. Now, what does this mean for? Remember that I motivated this talk by saying that we got to take something from the left end of the power spectrum and put it back into the right end, which is where the particle heating is determined, the ion and electron heating is determined. This can be done using microphysical studies, and people have done it. And it turns out that the ion to electron heating ratio can be written as a formula. So the expression on the top is the ion to electron heating ratio, and it depends on the slow to unfailing drive power. Some microscopic. So the left expressions capture the macro scale physics, the right expressions capture the microphysics. Okay. So now, as we know what the slow to unfailing ratio is, we can express this in terms of the Maxwell's and Reynolds stress tensors. And remember that Maxwell's and Reynolds stress tensors are something that can be computed even in global simulations. So locally, when we're modeling two temperature MHD, for example, we can locally infer what the slow to unfailing ratio is, or what the ion to electron heating ratio is, depending upon what the stresses are locally. And for people interested in what exactly the numbers are, how does the ion to electron heating ratio change depending upon your global conditions. As I said, it primarily depends on the shear. And on the right, what we are looking at is the electron heating fraction inferred from this as a function of plasma beta for different shearing rates. So the plasma beta is something which is effectively an effect of the microphysics. The shearing rate is the global scale physics, and as you see, different shearing rates have different ion to electron heating ratio, fraction, as we would put in the subgrid model. So on the right is effectively a subgrid model that is consistent with the global scale physics of driving in an accretion flow, and I can put this back into a global accretion flow and infer modern electron thermodynamics to capture spectral images based upon the global scale physics. So yeah, exactly that. Now we have an ion to electron heating ratio based upon what physics of the global scales are to the red to the left end of the spectrum, what the physics of the global scales are on the right end of the spectrum, the kinetic scale physics. Okay, so what would it take to put this back into a global TRMHD simulation? So these quantities in a local shearing box, whenever we study turbulence in a local shearing box, they are statistical numbers, right? So the slow to unfailing wave varying ratio involves averaging over characteristic scales of the problem of the Maxwell's Reynolds stress tensors, and the shearing rate is something that we put in. So when this study represents a very locally zoomed in patch of an accretion flow, which is particularly saying that there is no other characteristic scale that is captured of the global simulation. So this is a scale-free problem. There is no scale of and there's no scale involved with gravity or anything with the accretion distance. The way to put this back is effectively to consolidate the scales of the local scale physics into the global scales. And as we can expect, if we want to consolidate these scales, scales bring in additional physics. So if we look at a turbulence at a much zoomed in section of the accretion flow without considering effects related to, for example, scales associated with gravity and the effects of vertical stratification. So if you add vertical stratification in a local shearing box, you get turbulent structures something like this in the center, right? So these are stratified shearing box simulations, the mid-plane regions are different from the polar regions. And in these setups, what is the numerical decomposition and how do these tie into the global simulation? It's something which is a little bit problem, putting this back into a global simulation or answering the question of how electron heating is caused globally in radiation flow requires answering these questions. Well, if we still want to infer what a first inference of what this subgrid model leads to the observational manifestations of the flow. The observational manifestations being the ion and the electron temperatures. You can do a semi-analytic calculation where you ignore the effects of the turbulence in the flow, but you say that it is a semi-analytic transport model which governs the accretion. You can still infer what the impacts of the subgrid global scale current would be in the ions and the electron temperatures, which eventually lead to the radiation, and this is what it looks like. So what I'm plotting is the ion to electron temperature as a function of plasma beta. This is something which is always used to extrapolate from the single temperature GRMHD, global GRMHD simulations to obtain images. And using semi-analytic computations, you can infer what the ion to electron temperature ratio is, and as you can see, global scale physics impact that. And the curves obtained in these are quite different from typically what has been used with inferences by the telescope. So these are basically self-consistent methods, issue methods of modeling thermodynamics in the systems. Okay,
so there was a regime where the ion, if you go back one, there was a regime at the bottom left where the ion temperature is actually below electron temperature, right?
So yes.
Do you believe that?
So if you put in the microphysics under consideration, if you put in collisionless tapping is what determines it, and if you act under the assumption saying that
so the answer is no.
No, absolutely. Low plasma beta is something else, but this is what the question is.
Yeah, sorry for the uninformed question, this is my field, but so the sign for Q, so if I guess the ion to electron temperature ratio, it increases with decreasing Q, but then when you have those formulas with the macrophysics and the microphysics, Q is on the top, so.
Yes,
how does that work?
I'm plotting the other thing. I'm plotting electron heating fraction there. So, so electron is on the top.
Oh, okay.
Sorry for the technical and therefore boring question, but what's your box size on this and what's your quality factor?
Quality factor is
your MRI quality factor.
So unstratified MRI, that's the linear mode, which means we are resolving it. The box aspect ratio is 4/4/1. There's no quality factor because it's a unstratified shearing box. So all you need to do is resolve the linear mode, and quality factor comes in when you do a global simulation.
I mean, I do shearing box simulations and quality factor actually is pretty important because it does tell you what you're resolving, so
Yeah, so we are resolving the linear mode.
okay, so you are resolving, okay.
That's the linear mode. And you see.
Right, see that, it's just, I have seen simulations which have under-resolved, in order modes that do still get that same structure, but bigger, it just.
Yeah, no, so the resolution of the effects of MRI is a important question because it actually determines the saturation, the amplitude of saturation of the stresses. But here what we are looking at is the slow to effective driving power ratio, which means that, oops. Yeah, so what we are looking at is the ratio of the stresses and that resolution dependence cancels out. So you do not need to worry about the amplitude, the ratio is always fixed, and that's all that matters. As long as you are resolving linear modes, that's fine. We have done high resolution simulations and make sure that slow to the driving.
Okay, so you have done resolution studies and this
Yeah,
is,
yeah.
or just, okay,
Yeah,
wonderful.
Decomposition, yeah.
I've just seen a lot, and this is because I do stuff with MRI and like multi-physics, and so I've seen a lot of under-resolved MRIs. It doesn't look like under-resolved MRI, but I always need to ask the question of what actually are we doing?
Yeah, so resolution actually points out two things here. One thing is there can be scale dependent couplings between the modes. So slow to effect waves, what we are looking at is the injection physics. Past the injection scales, there's a coupling physics, right? So as far as we've seen, coupling is weak between the noble modes because these are anisotropic plasmas, and they are energetically decoupled, which is why in the first place we are able to extrapolate effect across scales. But yeah.
And I'm sorry if you said this, very, very cool talk, and so I was taking a lot of notes, so I might have missed this. Because I know you were talking a little bit about stratification. How do you expect stratification to change any of this, if at all?
Well, there's a Parker mode, Parker instability. So none of that is captured here, number one. Number two is that stratification brings in helicity. So this does not have any helicity in it. Helical driving changes things, both at the macrophysics and the microphysical scales, because helicity barrier, there's something known as the helicity barrier effect that's seen in the solar wind, for example, and that changes the ion-to-electron heating fraction at the microscale. So those are like bigger open questions with global simulations that you see helicity cascades and can be connected to microphysics, can they be extrapolated. So so extrapolating across scales is again particular to processes and particular to the physics influence. Okay, so I wanted to summarize after I will just tell you again the biggest takeaway I would like you to after this talk is the fact that MRI is expected to be scale determined. Thank you.
So you're arguing that the field is azimuthal, maybe this is related to the stratification you're just discussing, but in say relatively strong colloidal flux situations, the saturated state is sort of B phi BR roughly equal amounts, right? There's this tilt angle between the field and used to measure quality factors and other things. Does that change? Do you get injection directly into alpha modes in that case, or is the physical situation basically the same?
So if the mean magnetic field is vertical, this setup in a stratified simulation, you expect all of them to be affinities.
Mhm.
But if you put in like stratification, as I said, like it might be something else, because Parker modes are very different. They're fundamentally compressed, like they're all in same stabilities, right? So that requires, in my view, a numerical computation. So as you can see in a stratified box, like there can be different normal mode decompositions in the midplane and in the of the midplane. So that is exploration to be done. There can be other instabilities, like there have been studies, particularly in the match state of accretion, that in the inner regions, it's actually magnetic relatively that causes the angular momentum transport, and there have been microphysics calibrations based on this. So yeah, depending upon what is causing the landscape transport. So putting this back into global simulations again, we basically need to make sure that we are seeing consistent Maxwell center stresses as we see in the shearing boxes in the global simulations as well. And I have done studies with global simulations related to this as well, and there are regimes, particularly same midplane regions, they follow Maxwell center stresses consistent with what is seen.
Sorry for,
Yeah.
thank you, just trying to understand it. So the formula that you wrote down of the injected power being related to ratios of Maxwell and Reynolds stresses.
Yeah.
That part could change depending on what you were discussing about different instabilities and so on.
Yes,
right?
yes,
Okay, great.
yes.
Thanks.
Yes.
You could still try to measure numerically directly, right? Which,
Yes.
how much power is in modes of pointing in different directions or things like that? Or-
Yes.
Okay.
Yes, absolutely. Yeah, but also the ratios of Maxwell's and Taylor stresses are a signature of the phenomena itself. Like,
Yeah.
you can analytically predict what it's going to be depending on the stratified box, and if it adds up to the what we see in the shearing box, it validates the box.
And that's, I guess, what I was wondering, so once given that formula, you could just sort of guess what those things are and know the answer, but the power that is in assigning the driving in the modes to being ratios of the stresses in that particular way. Okay, thanks a lot.
So that is where the scales also come in. Like if you're looking at a global simulation, what is the coherence time scales basically of the stresses, because things come and go, right? So yes.
Other questions? If not, we can thank Kaushik again.